Welcome to this talk. My name is Jan Meset and I'm working for Dassault Systèmes. Today I want to talk about Stellar Physically Correct, the Global Illumination renderer of Dassault Systèmes. And I want to talk about how using Intel oneAPI Rendering Toolkit technologies improves the productivity of Stellar Physically Correct. Let me start with a brief introduction of the purpose of Dassault Systèmes. Dassault Systèmes provides business and people with 3D experience universes to imagine sustainable innovations capable of harmonizing product, nature and life. Harmonizing product, nature and life is how we define sustainable innovation. Our purpose is based on the premise that in the 21st century, with a global population of 7 billion people, we just cannot produce and consume in the same way that we did in the 20th century when the population was just 2.5 billion. A product cannot be sustainable if its impact on the environment and on society has not been thought through. And conversely, product design can be improved by observing nature and other living creatures. In brief, we are committed to using virtual worlds, which we call 3D experience universes, to help better understand and simulate how products, nature and life can interact in harmony. This is one reason why Dassault Systèmes is named a 3D experience company. Dassault Systèmes serves its customers in 11 industries via 13 brands. Some of these are very well known to the audience, like CATIA, SolidWorks, 3D Excite and 3D VR. The applications Dassault Systèmes provides to its users are located in the 3D Experience platform, which allows for efficient exchange between these applications. The 3D Experience platform apps are based on a set of common technologies. One of these are the 3 render engines provided by Dassault Systèmes. Real-Time Online, a WebGL-based real-time renderer, Real-Time Native, based on OpenGL and Vulkan, and Stellar Physically Correct. This talk focuses on the Stellar Physically Correct engine, which is HPC and cloud capable and allows for highly realistic rendering and best possible quality. At Dassault Systèmes, various cases exist where physically correct results of rendering are required. In design and engineering, Global Illumination rendering helps people generate renderings they can trust, because they predict the real-world impression very well. Rendered images are often the basis for important product decisions, covering especially the following 4 areas. In color and trim, people need to decide on colors and materials to be used with the products. For this, it's very important to see the interplay of these different materials and get a feeling for the lighting and the impression of the overall product. Here, full global illumination rendering is particularly important because of the intricate material effects that need to be simulated, like subsurface scattering, transparency, and many others. The second case where global illumination is very important is Class A surfacing. In this case, the smoothness of the surfaces, their aesthetics, and also modeling errors need to be checked and validated. Another case where global illumination is particularly important is light design. In today's products, more and more lights are being embedded, and simulating the interaction of those lights with the product is something that only a full global illumination rendering can do. The fourth case for design and engineering on this slide is flush and gap. In flush and gap, people need to check whether the gaps between the different parts of the product still look appealing, or whether you can, for example, see the interior through those gaps. But Dassault Systèmes is not only targeting design and engineering, but also provides solutions in the area of marketing. In marketing, where people want the most appealing rendering results, global illumination rendering is especially relevant for the following cases. For creating images or layers for product configurators, or for creating potentially high-resolution renderings for print, web and video campaigns. Let me give you a bit of background about Stellar Physically Correct. The Dassault Systèmes Global Illumination renderer Stellar Physically Correct first became productive in Bank Speed Shot, an application for product visualization, in 2014. It was later integrated into other Dassault applications. In 2017, development of an alternative renderer based on wavefront rendering was started. It became productive in the 3D Experience platform in 2019. It can run on CPU and GPU. Fundamentally, Stellar Physically Correct is a path tracer, implementing direct light estimation and multiple importance sampling. Currently, it supports 2 types of materials. First, the Dassault Systèmes Enterprise PBR material, which is an Uber material. The material ensures best possible consistency with the real-time renderers also exposed on the 3D Experience platform. And second, it supports measured X-Rite AXF materials to maximize the level of accuracy. Stellar Physically Correct supports local and distributed rendering, also in clusters, for interactive and batch rendering. For interactive rendering, special care is taken to minimize latency. As of today, the majority of users use Stellar for local rendering. But we see that distributed rendering becomes ever more important. More and more people use 3D content, also on low-power devices like mobiles and tablets. Since these users still want optimal rendering performance and quality, rendering is done in cloud environments more and more, often also using compute clusters. The new Stellar Physically Correct renderer is implemented as a wavefront renderer, meaning that it traces sets of rays instead of recursively following one ray after another. To work optimally, it makes use of various Intel oneAPI rendering toolkit solutions. We use Intel Embry for high-performance ray tracing intersections. We use Intel OpenImage Denoise for high-quality CPU noising. And we use Intel threading building blocks for efficient utilization of multithreading. In the following slides, I will outline why we chose Intel Embry and Intel OpenImage Denoise. Stellar CPU GI is tuned to optimize rendering performance. Besides choosing the right algorithms, this of course implies that we want to maximize CPU utilization. While rendering scenes like the one shown in the image in the bottom right, which shows the base of a robot arm with an emissive material, CPU utilization is fairly above 90%. The graphs on the right show how well Stellar CPU GI scales across different Intel processors with varying core counts. Roughly, the performance of Stellar CPU is proportional to the amount of available cores and their clock frequency. The combination of efficient algorithms and good hardware utilization makes Stellar CPU GI quite competitive with respect to rendering times. Achieving such high CPU utilization and scalability certainly needs a lot of coding and optimization work. While we are certainly capable of achieving great numbers for single CPUs, achieving such great numbers across multiple CPUs and even CPU generations with varying instruction sets and cache sizes really requires a lot of work. We are very happy that Intel provides the fully optimized ray intersection library Embry exactly for this purpose. This frees us from the efforts to optimize on different CPUs, allowing us to concentrate on the algorithmic challenges of global illumination, which are hard enough to keep us very busy. I want to illustrate another advantage of Intel Embry based on a real example. The brand 3DEXCITE offers software and services to build web-based product configurators. Especially for highly configurable products like cars, where numerous aspects like the paint, the rims, and many other aspects can vary, such a configurator is not an easy endeavor. Web-based product configurators for such highly configurable products are often realized via layer compositing. For every configurable option, here for simplicity, only the body color and the rims are configurable, and for every camera view, a layer is rendered and stored. When a user chooses a specific configuration in the web-based configurator, all layers corresponding to the current configuration are fetched and are composited with the compositing engine, as you can see on the screen. The results displayed in product configurators need to match reality very closely, as they are a basis for decision making. Even more in times like these, where access to the physical product is even more restricted than before, and actually where the chosen product configuration may not even have been produced yet. As such, it really makes sense to compute these layers via Global Illumination renderers. While the layer approach works fine in most cases, one day we stumbled over a problem which manifested as unacceptable disturbing black pixels, as you can see on the zoomed-in version on the bottom here. After some investigations, it turned out that the problem were pixels in the alpha channel of the layers, which were slightly off. They should have been perfectly white or opaque, but in fact they were slightly gray and as such transparent. Further investigation showed that the underlying problem came from the ray triangle intersection computations. While the theory behind computing intersections of triangles and rays is actually very simple, robust implementations are actually far from trivial. There are two potential numerical problems to be coped with. One of them is where the angle of incidence of the ray with respect to the triangle is small, making it numerically hard to compute accurate intersection points. The second potential numerical problem occurs when intersection points are very close to triangle borders. In such cases, it can be hard to identify whether the intersection is in fact still inside the triangle or outside already. And it turned out that the second problem caused the slightly wrong alpha channel. Luckily for us, Intel Embry provides a special intersection mode which computes intersection a lot more robustly. Using this mode solved the problem at hand at a performance cost of only 3% on average only. Implementing such a technique ourselves would certainly be possible, but a lot of tedious work. We are happy that Intel did the job for us and all others using Intel Embry. In the following slides, I want to illustrate why we chose Intel Open Image Denoise. Denoisers are very helpful to compute low-cost but high-quality images. Use cases for such low-cost images create in the ideation or design phases of product development, but also in marketing, especially if a huge amount of variations of the product exists. The images on the slide highlight ideation cases. The car interior on the left shows an early draft or prototype of a car interior. With a limited level of sophistication of the geometry and materials in this early conception phase, it is perfectly suitable to have slightly limited rendering quality as long as fast rendering quality and compute times support the fast design iterations. The architecture renderings on the right are from Home by Me, an online 3D space planning service developed by Dassault Systèmes. Users sketch their buildings, including existing or new furniture. They want to get a realistic impression of the planned space, which requires global illumination rendering. Yet, to offer the service at a low cost, rendering is also required to finish in a relatively short amount of time. Global illumination methods based on Monte Carlo integration like path tracing produce great images at the cost of relatively long render times. Computing images with imperceptible noise levels can easily take minutes or even hours, which is certainly too much effort if many images need to be computed. Therefore, image denoisers are used to reduce the time to compute noise-free images. Instead of shooting thousands of samples per pixel, as in the image you can see on screen now, you can shoot tens of samples per pixel, as you see in the image on the right. Apply a denoiser, and thanks to its intelligence, it produces a smooth, noise-free image that resembles the intended result very closely. Let me show this by some zoom-ins. So now here you can see on the bottom, on the left, a zoom-in of the image that rendered for many minutes, and on the right you see the still noisy image that rendered for just a few seconds. If you now apply a denoiser to the images on the right, you can see that it also looks very, very nicely and smooth, almost resembling the one on the left side, which took roughly 100 times as much time to compute. In the last years, denoisers based on deep learning became state-of-the-art. To ensure good results for CPU rendering, we also built and trained our own deep learning-based denoiser at Dassault Systèmes. The images that you see on the screen originate from it. As the images illustrate, starting from few samples per pixel, it produces quite good results already. As you can see, especially in the insets, even the images with 16 samples per pixels allow a designer to get a good feeling of the lighting inside the car with very, very limited rendering time. With 256 samples per pixel, results look actually quite smooth and convincing already. But we also noticed that with only few samples per pixels, results are certainly still far from perfect. You can see in the images on the left bottom that a lot of details are missing. We noticed that Intel Open Image Denoise targeted the same idea we had with our denoiser. But we found that it produces significantly better results when only few samples per pixel were used. So here, please take a look at the images at the bottom left. You can see that these contain a lot more details as we saw on the previous slide. Therefore, we decided to include Intel Open Image Denoise to allow integrating applications to choose these great results. The results shared in this presentation are the result of a long-lasting strategic partnership between Dassault Systèmes and Intel, aiming at improving the efficiency of design, engineering and visualization tools developed by Dassault Systèmes, allowing our customers to take better decisions for harmonizing product nature and life. To recap the talk, I showed 3 examples where the Dassault Systèmes Global Illumination renderer Stellar Physically Correct profits from using Intel oneAPI Rendering Toolkit technology. Using Intel Embry to achieve optimal ray intersection performance on different CPU generations, and to optimize the accuracy of computed intersections. In addition, using Intel OpenImage denoise to provide high-quality denoised images, even from images with very few samples per pixel. I want to thank the Intel team for the great support and commitment that you provided to our long-lasting strategic partnership over the many years. Thank you very much for the support. It's been a pleasure working with you. With this, I come to the end of my presentation. I hope you found it inspiring. For the future, I invite you to try Stellar Physically Correct in the Dassault Systèmes products and to find out more about Dassault Systèmes by visiting our website. I also invite you to check out how Intel oneAPI Rendering Toolkit can help you with your own software by visiting the Intel websites. Thanks for listening.